In the last few lectures, we've introduced integral vector calculus and differential vector calculus. Specifically, we introduced in differential vector calculus diff, grad, and curl for vector and scalar fields. We introduced in integral vector calculus the line integral, the surface integral for evaluating fluxes and circulations through closed surfaces or around closed loops. When we introduced differential vector calculus, integral vector calculus, we used rectangular coordinates, Cartesian coordinates, as our example coordinate system. And so our diff, grad, and curl were expressed in rectangular coordinates. Our integrals, line integrals, surface integrals, expressed in rectangular coordinates. That's great for some problems. If I have a rectangular array of charges, perhaps in a crystal, rectangular coordinates are great. It's not so great for other problems. Supposing you have a problem where you've got a spherical distribution of charge. You don't want to be using rectangular coordinates. If you've got a cylindrical distribution of charge, you don't want to be using rectangular coordinates to solve that. In this class and the next class, we're going to move on from rectangular coordinates and div, grad, curl, line, surface integrals, and rectangular coordinates to cylindrical coordinates. That's this class. Spherical coordinates, that's going to be the next class. In each of these classes, I'm going to walk through how to firstly introduce those coordinate systems. What is the language of those coordinate systems that parallels x, y, and z? What are the unit vectors that parallel x hat, y hat, z hat? Then we're going to talk about div, grad, and curl in these coordinate systems. What do div, grad, and curl look like in cylindrical and spherical coordinates? And we're going to talk about surface integrals, line integrals, volume elements. What do those things look like in cylindrical and spherical coordinates? So that's the plan. It's the plan for today with cylindrical coordinates, plan for next class with spherical coordinates. So this slide introduces the cylindrical coordinate system, which is the coordinates rho, phi, and z in terms of the rectangular coordinate system, x, y, and z. So on the plot here, here's x, here's y, here's z. Here's the three axes of rectangular coordinates, and here's the origin. Onto this plot, I've imagined a field point. It's located up here, or just some point in space located up here. And I've imagined the vector from the origin to that field point, or that interesting point. I called it r, the vector r. And if we like, we could express the vector r in rectangular coordinates using the rectangular coordinate unit vectors and the components of r in the directions of x, y, and z. That would be our rectangular coordinate language. What we're going to learn how to do is express the location of that point, that interesting point, that field point, say, in the language of cylindrical coordinates, which is this language of phi, rho, and z. So here's the phi, here's the rho, and here's the z. So what are rho, phi, and z? Let's see if we can answer those. I'll start with rho and then go to phi, then go to z. On this sketch of r and the rectangular coordinate systems, imagine that we project r's shadow with some bright light above r onto the xy plane, the horizontal axis. Here's the shadow. The length of that shadow, the projection of r onto the xy plane, that's the coordinate rho. That distance, that length is the coordinate rho. The angle of that shadow the angle of that shadow measured with respect to the x-axis, measured away from the x-axis towards the y-axis. That's the coordinate phi. So those are two of our cylindrical coordinates. And then the third coordinate is the distance of this point above the xy plane. That's this z distance, and this is common to both rectangular coordinates and cylindrical coordinates. So this is the same in those two coordinate systems. So that's how rho, phi, and z relate to x, y, z. That is how the vector components specified by rho, phi, and z relate to the vector components specified by x, y, and z. Downstairs here, I've written how to translate from one of these systems to the other one of these systems. So on the left is from cylindrical coordinates into rectangular coordinates. On the right is from rectangular coordinates into cylindrical coordinates. These are the two dictionaries, like French, English, English, French dictionaries. The translations, which are given by these little formulas, are really just based on one right angle triangle. Here it is the right angle triangle that lies in the XY plane. Here's the right angle. Rho is the hypotenuse of it. X is the adjacent of it. It's adjacent to phi. And Y is the opposite of it. It's opposite Y. So for example, the X coordinate in rectangular coordinates is related to the spherical coordinates. It's the adjacent side of a right angle triangle with angle phi and rho is going to be x equals rho cosine phi. And because the y side is the opposite side of this right angle triangle, it's y equals rho sine phi. And so that's the basis for this translation here. And of course, the translation for z is straightforward. Z in rectangular coordinates and cylindrical coordinates is the same. So z equals z, whatever that means. The translation in the other direction, again, is right angle triangle, Pythagoras' theorem. Rho, the hypotenuse, which is opposite the right angle, is just square root of the sum of the squares of the adjacent and the opposite side of the triangle. Then inverse tangent, arctangent, the ratio of the opposite and adjacent will take you to the angle phi. So that's introducing the cylindrical coordinate system and the rho, phi, z in terms of the rectangular coordinate system and the language of x, y, z. Okay. In rectangular coordinates, we introduced unit vectors, x, y, and z, that were of length 1 and were mutually perpendicular to each other. I've sketched them over here on the left. In cylindrical coordinates, we also have 3 unit vectors. They're also of unit length, length 1, and they are also mutually perpendicular to one another. I've sketched them over here on the right-hand side. So we've got a set of unit vectors in rectangular coordinates, a set of unit vectors in cylindrical coordinates, and these unit vectors kind of span the three-dimensional spaces, but in two different languages, rectangular and cylindrical. It's these unit vectors that will be used to represent some arbitrary vector. So we used to represent an arbitrary vector in rectangular coordinates by its components, ax, ay, az. Now we're going to represent some arbitrary vector in cylindrical coordinates by its components rho, phi, and z. That's what are depicted upstairs here. So this is introducing these new coordinates. Couple of properties about them, and then how are they related to one another, that question. The rectangular coordinate unit vectors are orthonormal. They have properties which we describe as being orthonormal. That is, their lengths are one and they are at right angles to one another. And so, for example, x dot x, dot product of a pair of x unit vectors, that's one. X dot y, dot product of an x and a y unit vector, that's zero. That's based on them being orthonormal. For the cross products, x cross x, remember cross product picks out perpendicularness. This is zero, but x cross y gives us the third direction. That's the z unit vector. So there's very similar properties for the dot products and the cross products and orthonormality of the cylindrical unit vectors. So they are a length one. They're at right angles to one another. So rho dot rho, as an example of a dot product of like unit vectors, is one. Rho dot phi as a dot product of two unlike unit vectors, that's zero. Rho cross rho, that's a cross vector product of two like unit vectors. Well, cross product picks out perpendicularness. These two vectors are the same, they're parallel, that's zero. Rho cross phi gives you the remaining unit vector, the z unit vector. And so in that respect, the relationships between the unit vectors and the orthonormality of the unit vectors looks very, very similar in rectangular and cylindrical coordinates. What about, we talked about how to translate rho, phi, and z to x, y, and z, and vice versa, but how to translate the unit vectors. So this is important. It's important because of a fundamental difference between x and y and z unit vectors and rho, phi, and z unit vectors. And the difference is as follows. No matter where you walk in space, the x and y and z unit vectors always point in the same direction. They're always fixed in the same direction. So they don't change. When you walk around in space, the rho, phi, and z unit vectors, so in general, they rotate. They turn as you walk around in space. They're not in a fixed direction. But that's a big difference. And the relationship between those two unit vectors therefore depends, and the directions that they point in, therefore depends on where you stand in space, because that will affect, the degree to which or not the the cylindrical coordinate unit vectors have rotated with respect to, say, the x, y, z unit vectors. So that's described in these relationships down here at the bottom. So the relationship on the left, again, this is based on the right angle triangles. I'm not describing in words, deriving this in terms of that right angle triangle on the horizontal plane, but it comes from the same place. This is the relationship on the left-hand side between the rho, the phi, and the z unit vectors and the x, y, and z unit vectors. And then the reverse is true on the right-hand side here. This is the relationship of the x and y and z unit vectors to the to rho, phi, and z unit vectors. If you look at, let's take the example of the right-hand side, but you could see it in the left-hand side too. If you recognize that the x and y and z unit vectors always point in the same direction, the rectangular coordinate unit vectors always point in the same direction, you see that the direction that the rho and phi cylindrical coordinate unit vectors will point in will depend on the angle phi. Because depending on the angle phi and the cosine and the sine of the angle phi, you get different mixes of x and y defining rho and phi. So this is what I mean by the rotation of the phi and the rho unit vectors in cylindrical coordinate unit vectors, whereas the x and the y and the z unit vectors, they're fixed in space. So that's a big difference. There was similarities. Orthonormality was a big similarity. All these patterns upstairs here, these are big similarities between the two schemes. Downstairs here, there's a big difference. Fixed directional XYZ unit vectors and rotating rho phi unit vectors for cylindrical coordinates. Okay. In this slide, I'm going to elaborate a little bit on this rotation. And to elaborate on the rotation, we're going to look at how much the unit vectors phi and rho, how much they rotate when you change the angle phi, the coordinate phi. So as you walk around in phi in cylindrical coordinates, so you're walking around the z-axis in cylindrical coordinates when you walk around in phi. As you walk around in phi, the directions of the rho and the phi unit vectors of cylindrical coordinates, they're changing, they're rotating on you. And the question is, by how much do they change? To quantify that, I'm just going to determine the derivative of the rho unit vector with respect to phi. That measures the change as you change phi, and the derivative of the phi unit vector with respect to the rho coordinate. That again will measure the change, the rate of change of the phi unit vector as you walk around the z-axis, as you change your phi coordinate. And so this slide is just to present that. I want to start without saying how I computed it by just giving you the bottom line. Over here on the left-hand side of this pair of equations, that's the rate of change of the phi unit vector with phi. So in this partial differential here, you're imagining how much phi changes, by what amount that phi vector changes as you rotate in phi. Same thing downstairs here. This is how much the phi unit vector changes as you move around the z-axis, changing phi. Partial differential of phi with respect to phi. I've done a calculation and I'm showing you that d rho d phi is not zero, firstly, and d phi, that's also not zero. In rectangular coordinates, those would be zero because those directions are fixed. For cylindrical coordinates, those are not zero because rho and phi rotate, they're not fixed. D rho d phi is equal to phi. So the rate of change of rho with respect to phi is determined by the phi unit vector. And a similar pattern here. D phi d, the rate of change of the phi unit vector with respect to phi, that's equal to minus rho. So the differentials of the rho and phi unit vectors are not zero, firstly, and those differentials are equal to, for the rho unit vector, equal to phi, for the phi unit vector, equal to minus rho. The way I figured it out is to use a relationship from the last slide. I just substituted in what phi is in rectangular coordinates, what rho is in rectangular coordinates. So these two little expressions here, this is just substituting in from the dictionary on the last page. Then I said, well, let me differentiate the term in parentheses upstairs here, differentiate the term downstairs here in parentheses. What happens when I differentiate the x unit vectors, the y unit vectors? Nothing happens in those cases. I've seen a mistake, though. These should be x. These are not x unit vectors. These are y unit vectors. So these x and y unit vectors here that I'm going to differentiate, those are just like constants. When you differentiate a function, it's multiplied by constant. These just sit there. Nothing happens to them. They're just going to multiply the differential of the functions in front of them. They themselves, if you try and differentiate them, they're fixed. They're not going to change. So the x's here appear as x's here, and the y's on the right-hand side appear as y's here. When I differentiate a cosine, I'm going to get a minus sign. when I differentiate a sine, I'm going to get a cosine. So this cosine phi becomes minus sine phi. This sine phi becomes my cosine phi. And similarly downstairs here. And then once I calculated these results of the differential, I just looked back at the dictionary and said, hey, look, well, that's curious. This guy here, that's phi. And this guy downstairs here, that's minus rho. And so it was a simple matter, once we knew the dictionary that related the cylindrical coordinate unit vectors to the rectangular coordinate unit vectors, to see what the differentials with respect to phi of the rho and the phi unit vectors is. And that's what I've carried out here. And the fact that these unit vectors don't vanish when you try and differentiate them with respect to phi is very important when we go to constructing divergences and curls, for example. So this is an important result. That is something completely new that was completely absent in the world of rectangular coordinates, x, y, and z. You don't have to worry in x, y, and z coordinates about the differential of the x unit vector with respect to x or y, or the y unit vector with respect to x or y. Those are zero. That's not an issue. Okay, this slide is a slide to help us more with integral vector calculus, perhaps. In integral vector calculus, when we got to specify line elements, and later on we'll see surface and volume elements. And also in integral vector calculus, we have to specify displacements through the field. So on this slide, I'm just introducing how we would specify a position of a point in cylindrical coordinates, and just comparing it with how we did it in rectangular coordinates, and how we would describe a line element in cylindrical coordinates compared with how we would describe a line element in rectangular coordinates. So this is just to remind us as we look at these relationships of the relationships between the two coordinate systems. That's all this picture is for. But on this picture, I am marking two important things that we want to describe on this overhead. And they are, I'm going to write down the position vector R in the language of cylindrical coordinates. We've done it in rectangular coordinates, but I haven't actually yet wrote it down in cylindrical coordinates. I'm going to write down a little line segment, line element, ds, in the language of cylindrical coordinates. We've done it in rectangular coordinates. We haven't done it yet in cylindrical coordinates. And so that's what I'm doing downstairs here. This is the vector R, the position vector R, and doing downstairs here on the right, this is the line element ds. Here I'm writing them down in cylindrical coordinates, and above it I'm reminding us of how we wrote them down in rectangular coordinates. So in rectangular coordinates, the position vector R, in terms of the x, y, and z unit vectors, is just those x, y, and z unit vectors multiplied by the x, y, and z components of R. A little different cylindrical coordinates. The position of this interesting point, this field point, R, explicitly in cylindrical coordinates is rho times the rho unit vector plus z times the z unit vector. So rho times the rho unit vector, that takes us in the direction of the rho, a distance rho. So this is, sorry about my writing, but this is rho times rho hat. And then z times the z unit vector, that takes us up here, takes us a distance z in the direction of the z unit vector. I'm doing this with my mouse and not with the pen, which I don't know why I'm doing that. But anyway, that takes us to the field point. So that's specifying the position of the field point in cylindrical coordinates. You might say what happened to rho. Rho doesn't, you might say what happens to phi. There's no phi in this expression here. There was all the coordinates in this expression up here in rectangular coordinates. So you saw x, y, and z explicitly. You only see rho and z explicitly here. Phi is embedded in this first term here. The direction of phi, the phi unit vector, depends on rho. So it's embedded in this little guy here. It's hidden, but it is implicit. If phi unit vector depends on rho. Okay, in cylindrical coordinates, when we wrote down a line element, we wrote down its components in the x, y, and z directions, and they were dx, dy, dz. And these are just mutually perpendicular directions. This is the corresponding thing in cylindrical coordinates. Now, as you might imagine, we're going to sweep out little distance not in x, y, and z with the x, y, z unit vectors, but in rho, phi, and z. We want to swing out in a little increment little increments in these three directions. For rho, it's easy. We're just going to take a step d rho in the rho direction, just like we took a step dx in the x direction. Actually, for z, it's easy. We're just going to take a step dz in the z direction, just like before. It's the same coordinate. So we took a step dz in the z direction. For phi, it's a little different compared to how we step in rectangular coordinates. D phi is not a step in a distance. D phi is just an angle. The distance that a step d phi takes you is the arc that step d phi swings out. And the arc is of length rho d phi. So this is the distance rho d phi, not d phi. You see here, every term, every component, the dx, dy, dz, the d rho, the rho d phi, and the dz, they all have units of length. So they're all in millimeters or centimeters or whatever the units are. So that's a important difference here. If I'm thinking about how do rectangular cylindrical coordinates differ from one another, this is another important difference that we have to be aware of. On the next couple of slides, I've got a reminder of surface and volume elements in rectangular coordinates. We just looked at line elements, the dx, the dy, the z. And then, so that's a reminder. Then I've got the volume elements and surface elements in cylindrical coordinates. So this is the introduction here. But just to remind us, we, on the last slide, said that if we want to sweep out line elements in rectangular coordinates, we take steps dx, dy, dz. If we want a surface element in rectangular coordinates, well, we can make surface elements that are at right angles to the x direction, the y direction, the z direction. Those surface elements I call DAX, DAZ, and DAY. The planes are at right angles to the x, y, and z directions. The vectors that represent them are in the x direction, the y direction, and the z direction. So those are these are the planes here, and their dimensions are these areas are swept out by these little steps, dx, dy, and dz. So, for example, this surface element daz, that's constructed by line element dx and a line element dy. If we take those two steps, we sweep out this little rectangle here. which is the line element, the surface element DAZ. And so I've written down definitions of the three surface elements perpendicular to the three XYZ unit vectors in this little table here. So DAX is created by steps in dy and dz and is in the direction of the z unit vector. And similarly for the day and the daz to construct surfaces that have their surface vectors in the direction of the three rectangular unit vectors. If we want a volume element, we just multiply, well, there's typo here too. I got a little bit of homework coming up and cleaning up typos. This volume element is just we construct a volume by taking steps in x, y, and z. And so its volume element is dx, dy, dz. That's what we got here. And it's this pattern that we're going to follow for the cylindrical coordinate surface elements and volume elements. But the real difference is just related to that phi, that step in phi that we took, where d phi was just a arc of a circle, an angle that we swept out. The distance that we stepped was actually rho d phi. So that's going to come in when we look at the area elements and the volume element in cylindrical coordinates on the next slide. Okay, so this is the same arrangement as the previous slide in terms of introducing area element vectors and volume element, a scalar, but it's for cylindrical coordinates rather than rectangular coordinates. On this plot over here on the left-hand side, I'm showing you the cylindrical coordinate surface elements. And over here on the right-hand side, the cylindrical coordinate volume element. The cylindrical coordinate surface elements and the volume element are built out of the little line elements in cylindrical coordinates. So they're built out of the d rho, the d phi, and the dz. Specifically, like if you want an area, you're going to multiply, you're going to build it out of a step in, say, the phi direction and a step in the rho direction. And if you want a volume, you're going to build it out of steps in all three of those directions, the phi, the rho, and the z direction. So that's how we're going to construct cylindrical surface volume elements out of the cylindrical line elements. So I just want to show you a couple of examples. Firstly, but just a couple of words about the figures. So if you look at this figure here, here's my representation of the line element, surface element dA rho. dA rho is the surface element whose surface element vector points in the direction of increasing rho. It's constructed from a little step in the other cylindrical coordinates, a step dz and a step rho d phi. These two steps sweep out little arcs, and if we take those two steps, we sweep out an entire area here, and that area is this dA rho. And then similarly for dA phi, that's pointing in the direction of increasing phi, dAz is pointing in the direction of increasing z, and they're constructed by taking steps in the two other directions. So for phi, it would be in rho and z. For z, it would be in rho and phi to construct those area elements. These are the three formulas that come out of them. This is the construction of the area element that's perpendicular to the rho direction, the surface that's perpendicular to the rho direction. So the vector points in the direction of increasing rho, and here's the same thing for phi. Here's the same thing for z. You notice this one little complication. Whenever you take a step in phi, the arc that you sweep out is rho d phi. So this is a rho d phi here, and this is a rho d phi down here. It doesn't appear in this area element, the phi area element, because you sweep that out with steps in z and rho. So those are the area elements. And then over here, it's the volume element. It's just the product of those three steps in rho, phi, and z that sweep out this complete volume that I pictured upstairs here. And again, the little bit of subtlety is that when you take a step in rho, d rho, the air length of the line that you sweep out is rho d phi. So there's a rho in here. This slide contains div and curl. No, this slide, start again. This slide contains div, curl, and grad, or in the order of the slide, grad, div, and curl in the language of cylindrical coordinates. We've met these guys in the language of rectangular coordinates, and now on this slide, I'm introducing them in the language of the language of cylindrical coordinates. So let's just walk through them. I'm not deriving them. I'm just walking through these expressions. I think the textbook has details how to derive them. It's not difficult to derive them. But I want to just walk through them and show you some of the differences they have compared to the same things, grad, div, and curl in the language of rectangular coordinates. So we'll start upstairs, I think, with the gradient. That's this guy here. This is the gradient of a scalar field, or what we'll later call a scalar potential. But a scalar field, the field is U. It's just a number field. It's not a directional field. And this is the gradient of it, which tells us about the slope of it. In rectangular coordinates, we wrote this as the x, y, z unit vectors multiplied by the partial differentials of the scalar field with respect to the x, y, z coordinates. It's very simple like that. And this expression is almost the same as the rectangular coordinate version, with the products of partial differentials and unit vectors, with one little exception in here. We've got a term for the of the gradient that's in the rho direction, where the partial differential of u is just with respect to rho. We've got a term in the z direction for the gradient in the z direction, where the partial differential is just with respect to z. But we've got a term for the component of the gradient in the phi direction, whereas the partial differential of u with respect to phi multiplied by 1 over rho. This originates in that difference of sweeping out arc lengths in the direction of rho, in the direction of phi, where phi is an angle, compared to sweeping out arc lengths in the direction of rho and z, where the rho and the z's are measured in units of centimeters, for example. One way of remembering this is just think about the units again. This is a gradient, a slope. The units in each of these three terms better be the same, right? So we have here, from this partial differential, kind of a inverse centimeters or inverse millimeters for the units. Over here on the right-hand side, we'd have inverse centimeters or inverse millimeters for the units here, for the partial differential with respect to z. We better get those units for this term for the phi gradient, and it comes from this 1 over phi here. So that's one way I remember that there's a 1 over phi factor in here. So that's the gradient. One little difference from rectangular coordinates, and one way of remembering that one little difference from rectangular coordinates is that this is an angle. These guys over here would distances in units of millimeters or centimeters. Um, then we got two ways we differentiate vector fields. We got the divergence of the vector field, we got the curl of the vector field, and so they're given here. This is the divergence. Um, Here, this is the curl. Again, I would be asking you to remember back to what those things look like in rectangular coordinates. They look similar, but a little simpler in rectangular coordinates is the answer. So remember, divergence is a scalar quantity. It doesn't have direction. So you don't see any unit vectors over here on the right-hand side in the divergence. That's just the same as rectangular coordinates. It's a scalar quantity. In rectangular coordinates, it was just the sum of the partial differentials of each component of the vector field A with respect to the X, Y, and Z components. Uh, uh, so, for example, there was a dAx by dx. There was a dy by dy. There was a daz by dz. It was the sum of those that was the divergence. It's more complicated here. At least it's more complicated for the phi term, and it's more complicated for the a for the phi term. And it's more complicated for the rho term and the phi term. And the origins of that complication are really related to, in a sense, the shape of a volume element, the shape of the surface that surrounds a volume element in cylindrical coordinates. It was simple shape in rectangular coordinates because that volume was a little cube that we made with dx, dy, and dz. But if you look at that shape in upstairs here in cylindrical coordinates, it's much more complicated. Again, I'm using a mouse and not the pen. Can't stop doing that. It's not very precise with the mouse. Look, this is the shape. It's not very precise with the pen either. This is the shape of the volume element in cylindrical coordinates. And for example, this is the side we can't see behind us here. This is kind of pointing back towards the origin. That face is smaller than this side over here that's pointing away from the origin. So that complicates the calculation of the net flux through that's emerging in that direction through this inside face and going to this outside face here. It complicates it because this face on the inside, this is really horrible. This face on the inside is smaller in area than this face on the outside. If these faces were the same size, this piece down here would just be a simple differential with respect to rho of A rho. But because these faces are different sizes, we have to account for that. And all this stuff that comes along with the dA rho by d rho, which is this rho here and this 1 over rho here, is to do that accounting. One way of remembering that there's a row upstairs and a row downstairs is, again, to get the units right. If you look over here, you've just got a partial differential of the z component of the field with respect to z. You can use that as a reference for your units. If you stick a row up here, you've got to stick a row down here to keep the units corresponding to this dAz by dz. So that's that extra factor there. That's a real complication for this face that points towards the origin, this face that's away from the origin. This term here with phi is a a little more complicated than in rectangular coordinates. It's got this 1/row, but that has the same explanation of this 1/row up here. That when you take a step in phi, you sweep out an arc of a circle that is rho d phi. And we needed that fact there. We need it down here too. Okay. So that explains this new expression for the divergence in cylindrical coordinates. Here's the expression finally for the curl in cylindrical coordinates. This also has the same sort of format, but is more complicated for cylindrical coordinates. Remember, the basic format of the curl, when you write it as a determinant, is that you put the unit vectors in the top row, you put the partial differentials in the second row, you put the components of the vector in the third row. But you see complications here. You see a complication such as this row here and this row here in the top row of unit vectors, this phi here in the bottom row of field components. And so I'll be honest with you here. I don't have a mental picture of exactly how those are originating. Like I kind of had the mental picture of how they originate in the curl and in the gradient. Sorry, in the divergence and the gradient, the two expressions above. I don't think I can put into words exactly the origins of these things. If I want to know the curl in cylindrical coordinates, I'm not remembering this. I'm looking this up in the book or looking it up somewhere at least. And so this is curl in cylindrical coordinates. It has the same basic form with the unit vectors and the partial differentials and the components of the vector, but it has a more complicated form because of the more complicated shapes of loops, basically, in infinitesimal loops in cylindrical coordinates compared to infinitesimal loops in rectangular coordinates. I just wanted to end this class with a quick example of divergence and curl of a vector field in cylindrical coordinates for a field that is most simply expressed in cylindrical coordinates. And the one that I picked is a very simple field in cylindrical coordinates. It's this guy here. It would be a bit more difficult to write it in rectangular coordinates. This field, A, is just equal to a constant, some coefficient that's fixed, times the row unit vector. So it's really a field that just reflects the direction of the row unit vector. And so if I'm looking down along the z-axis on the xy plane in cylindrical coordinates in this slide. If I look at the field at any points in that xy plane, if I'm walking along the x-axis here, then the row vector is pointing along the x-axis, and I just see this constant field pointing along the x-axis, not changing its size. If I look along the positive y-axis, the row vector points along the positive y-axis, and I just see that constant field, A, along the positive y-axis. And then in any other direction, right, I see a constant strength field as I walk in any direction, any phi that I choose. It's always just pointing away from the origin, which is the direction that the phi unit vector points in. So that's what the field looks like as drawing field vectors. If I wanted to draw the field itself via field lines, which is more traditionally what we would draw, here's the field in terms of field lines. You see all the field lines are emerging away from the origin because the field always is pointing in the row direction away from the origin. You see more and more, if you were to walk further and further out, you see more and more field lines appearing, so that the strength of the field, which is related to the density of the packing of the field lines, the strength of the field is constant. Remember, this is just a constant times a row. So this is what the field line pattern starts to look like. if we go on to the next two slides, just to wrap up here today, I'm going to show you what the curl and the divergence of this particular vector field is. This is an evaluation of the curl, and on the next slide, I'll be evaluating, sorry, this is, I've got vector calculus dyslexia. This is the today. This is the divergence calculated for this vector field. And this next slide will be the curl calculated for this vector field using those formulas that I introduced for divergence and curl explicitly in the language of cylindrical coordinates. Okay, so here's our field upstairs, very simple field. Let's see if we can calculate for this field the divergence of this field. So here's our general expression for the divergence. This is the dot product of the del vector operator and the field. We wrote that out and talked about it in cylindrical coordinates. Like rectangular coordinates, it's got a bunch of partial derivatives of the field components. So the field components now are a rho, a phi, a z. The partial differentials are now with respect to rho, phi, and z. But it was a little bit more complicated. Here's a complication, and here was a complication. We mentioned why those complications arise. But anyway, what have we got to do? We got to substitute in for a rho, for a phi, for a z, for our field. Our field is just c in the rho direction with no component in the phi direction, no component in the in the z direction. And so I'm just going to substitute that this guy here, that's c, and then this guy here, a phi, that's 0. And then this guy here, that's az, that's 0. And so that's what I did here. This is my c. This is where I had substituted in 0 for these components. So their partial differentials vanish. This row here was not part of the field, remember. This is this row that appeared because of the funny geometry of volume elements in cylindrical coordinates. So now I really, once I put in the field, I've just got to do this calculation, which is the partial differential of, with respect to rho of c rho, which because c is a constant and rho is the variable here that we're differentiating with respect to, this just gives a factor of c. So this bit here is just the c, and then I've got to multiply by the inverse of rho, or divide by rho. And so here's the divergence. This is a field we've discovered that has a divergence. It has a divergence everywhere in space, which means that there's new flux being created everywhere in space. So there are beginnings and ends of field lines for this particular vector field, and they're being created everywhere through space. And that was probably best shown in the diagram I made for the field lines. There were field lines originating from close to the origin, field lines originating further from the origin, because there's flux originating from close to and far from the origin. There's flux originating everywhere. The amount of flux, the density of new flux is falling off with the distance from the origin, but the amount of space is growing with the distance from the origin. And that yields the field pattern that corresponds to this vector field here. It's a field that has a divergence everywhere. If it was an electrical field, there would be charge everywhere in a certain distribution to create this field. Last slide, I promise. This slide, we're going to not calculate the divergence of this field, we're going to calculate the curl of this field. And so we want to go ahead and calculate the curl of this field in cylindrical coordinates because this field was very conveniently expressed in cylindrical coordinates. So here's the general representation of the curl, the cross product of the del vector operator and the field that we're interested in. And here it is expressed in cylindrical coordinates, so we'll get to love. Again, has the usual form, a row unit of unit vectors in the top row, partial differentials the second row, field components in the third row, but there's these little complications due to the cylindrical coordinate nature of this coordinate system, with the rows in the top row and this row downstairs here in the bottom row. Anyway, our job is to feed in this particular field into this general expression. So feed in the components, a rho, a phi, a z of this field into this general expression. Well, look, this field points just in the rho direction, and its component in the rho direction is c. That's this guy here. Has no component in z, has no component in phi. That's these two zeros here. And so now we just got to compute the determinant of this little matrix here. You can see that lots of things are going to be zero. We've got partial differentials of zero. We've got partial differentials also of a constant. In fact, we're not differentiating anything other than a zero and a constant, and those are all going to be zero. So every term in this determinant has come out to be zero. This is a curlless field. There's no rotation of the field. There's no circulation of the field. You see this in the field line pattern or this drawing of the field vectors, that the field lines are not rotating clockwise or counterclockwise. It's a curlless field. So we've just met another important field, this field that's described by C times the rho unit vector. It's a interesting field as an electrical field. I don't think it's interesting as a magnetic field. It's a field that possesses a divergence, a source of flux everywhere in space. It's a field that has no curl, zero curl everywhere in space. Just to wrap up then, we've been talking about cylindrical coordinates. We've talking about the representation of curl, div, and grad, line integrals, volume integrals, and cylindrical coordinates. We had to define the cylindrical coordinates, the rho, the phi, the z. We had to define the unit vectors, and we noted some interesting features of the unit vectors in cylindrical coordinates. We had to define surface, area, and line elements and volume elements in cylindrical coordinates, and we noted some interesting features of those. Next class, spherical coordinates.